Hello, my name is Lucas, and I will present some of the progress I've done in the direction of adaptive isogeometric phase field modeling of the Canhilliard equation. I essentially work on interface problems, and usually interfaces uh, bring several numerical challenges because this interface move, merge, and split. And so one of the objectives of my work is to be able to provide a robust framework in order to capture the evolution of these interfaces in let's say, various engineering applications. For that, I use the so-called phase field methods, which regularize an a priori discontinuous interface, resulting in a smooth and continuous transition between these phases, which eases the resolution of the PDEs. Of course, there are some challenges that come from using phase field modeling, and some of them we're trying to tackle. So we will see. I will present some of the things we are doing in this direction. In this context, isogeometric analysis provides an optimal framework to model higher order problems because by construction, we can achieve by the construction of a specific um, basis, we can achieve the desired inter-element continuity. In this case, just by using quadratic B-spline based basis functions, we can meet the C1 continuity requirement of the Canhilliard equation. Some previous works in this direction regard adaptive schemes on 2D multipatches, also in the context of the Canhilliard equation, and brittle fracture models also in the higher order sense. Few words on the Canhilliard equation. This equation basically models the phase separation of immiscible fluids, and the strong form of the equation is obtained by applying mass conservation on a mass flux, and this results in a time-dependent fourth-order PDE with a set of boundary conditions and an initial condition on the solution field C. Now, also a couple of words regarding the double well potential F. The minimization of these free energies what drives the dynamics of the solution, and as we approach the binodal points, which are the two minima of this double well potential, we see the formation of equilibrium phases separated by these phase fields, by the interfaces. Very briefly, the continuous problem of the weak form, which evidences the need of using, let's say, at least C1 continuous basis functions. And with this, we will maybe move to some more funny images. These are basically, this is one of my first results of the project, and it comes from, let's say, the first steps of my research, which involved the implementation of this equation in the Gizmo library together with, let's say, some collaborators. I did this in the Gizmo library, which is a C++ library, let's say, with a big focus on isogeometric analysis. And as you can see here, we see two clear equilibrium phases in red and blue, and these are separated by the interfaces, in this case represented by contour surfaces, because it was easier to, let's say, visualize. Now, one of the challenges of phase field modeling is the fact that one needs to be sufficiently fine across the phase field, across these interfaces, in order to be able to resolve them well. Because, as I mentioned before, if you remember, these interfaces are continuous, but they are rather steep. So one needs to basically resolve them with enough accuracy. For that reason, when we go to higher dimensional problems, like in this case 3D problems, we need to basically be very fine, and that has a very high computational cost. And this essentially motivates our work in the direction of adaptive schemes, because what we want to achieve is to have very fine discretizations across the interfaces, and everywhere else in the equilibrium phases, we can essentially be coarser in our discretization. Among the many bases that there are on the literature for using adaptivity in the context of IGA, mm, we opted for the truncated hierarchical B-spline B-spline basis, and this is because these bases enable this refinement in any direction. They keep very nice properties from the hierarchical B-spline basis, and essentially through a truncation we are able to recover the partition of unity, which is let's say ideal for their use in numerical schemes. Of course, these bases can be constructed in multiple directions, and here I'm showing an example of a tensor product basis versus a THB basis, and in 2D. And as you can see, the use of THB basis allows for refinement in any desired area, let's say, of the domain. So now, since we have the basis for refining and having our local, let's say, features and local refinements wherever it's needed, I will also give a few notes on the adaptive admissible refinements loop that we use. So we solve the equation, the Canihilert equation, and then the next step, once we solve the equation, is to mark the elements that need to be refined. For that, we basically do this marking based directly on the numerical solution, and whenever we are within a certain interval, we refine, because that will mean that we are basically on an interface, so we need to be fine, and elsewhere we will coarse. Now, once we mark the elements for refinement, we also make sure that this refinement is admissible, and that means that we will, let's say, aim for having a refinement that causes the mesh to be graded, and that let's say very coarse levels do not interact with very fine levels of our mesh. And here I have a rather academic example to show how this admissible refinement scheme functions. And so, if we hypothetically had an element marked like the one I'm showing on the slide, we essentially check its support extension, and then we mark elements in the T neighborhood, which is the intersection of the support extension, which is this gray area, with the elements in the parent domain. And you see these elements are the three elements that I additionally marked for refinement. And then we do this in a recursive fashion, so we also check the support extension of the newly marked elements to indeed ensure that we have an admissible refinement. And from marking this small element in the beginning, we end up with this final element marking, which results in such a mesh. This, of course, is repeated every time we solve the equation. We mark and we see how our solution has evolved in that time step. And this produces these kind of results. So basically, as you can see here, I'm starting from the same initial condition, and you see that both the adaptive, the THB solution, and the tensor product solution produce the same numerical result. Now, one of the, let's say, challenges also of this work recently has been the fact that the Canhilert equation doesn't have a known analytical solution, and we wanted to basically study the accuracy of our adaptive schemes in terms of numerical convergence. And for that, we started by a work in the literature that uses an equation that varies harmonically in space and time to first test, let's say, the correctness of our implementation. And we did that through as I said, manufactured solution that we plug in directly into our equation, resulting in a forcing term that is then added to the formulation. We achieved, so these are the results from the literature, and we achieved the expected convergence rates. This GA stands for the generalized alpha scheme, which is the time marching scheme of our solver. And we achieved both the expected convergence rates for both space and time, using in the temporal convergence slightly different equation by changing the phase of the cosine functions, but essentially we obtain the expected convergence rates. Now, of course, this is this was a good result, but in the case of our adaptive schemes, if you see this function, most of the domain is occupied by the interfaces, and so we have very little regions where we can be coarse and let's say profit from the fact that we're using these adaptive schemes. So let's say that this is not the most ideal function to study. How accurate our adaptive scheme is with respect to our tensor product solution. And so we opted for another type of function, which is, let's say, that meets all the requirements in order to carry out this study. And this is a hyperbolic tangent-like equation, which essentially has these two equilibrium phases representing, let's say, well, the equilibrium, the areas where we have the equilibrium, and then the equilibrium phases, and then we have this steep transition between them, which could represent the phase field. And these essentially results in such meshes, no, where we have very fine discretizations or fine discretizations across the interface, and coarser discretizations elsewhere, wherever we are in the equilibrium phase, which is either the red or the blue. Of course, this using adaptive meshes saves a lot of degrees of freedom with respect to the tensor product, and that obviously has an impact in the computational times. But we will first focus on the first results that we have obtained in this direction, because this is a work in progress in the end. So we basically run this convergence study for both the tensor product and the THB example, and we did that for quadratics. Actually, sorry, because this video is running while this one has stopped. And basically, we achieved the expected convergence in both schemes. Actually, we see that if we do a comparison of the L2 error versus the number of degrees of freedom for the same level of accuracy, we're able to to have much less degrees of freedom in the adaptive case. I also experimented with a more rather romantic shape and try to also carry out this convergence study in the same way. Also, this is a hyperbolic tangent-like equation. And well, again, you see that we refine only wherever it's needed, so across the interface. And the meshes are quite nice to see, but the results are rather a bit more difficult, just like love. And yes, as I said, this is a work in progress, and there is probably uh, a lot of things to consider here, because also the marking of the function plays a role, like the way we mark for the refinement in this case, and probably the limits for the refinement are, let's say, not ideal in this case. But again, this is a work in progress, so we hope to have better results soon. Some conclusions. So basically, yes, we have a framework that allows us to have adaptive, multidimensional simulations. We are testing the numerical convergence of these schemes, also hopefully for soon for higher order basis functions. And then also, as I showed, we have significant degrees of freedom savings, which obviously has an important impact on the computational times. With this, I conclude my presentation. I thank you very much for your attention. And I encourage you to stay tuned to see some updates from my work and also from the work of my colleagues from the GECKO Doctoral Network. Thank you very much. Ciao, ciao.